Well, let's ask if we can go further than what we've got so far, and also kind of keep track of how far we've gotten. And of course, remember the original motivation for this is most of it is that it's just fun. It's just really fun to create such incredibly, unimaginably huge numbers. But the deeper motivation is that we've actually encountered some really, really important deep concepts already: recursion, diagonalization, the idea of starting arithmetic with a successor function and how you can get out of that. And it even goes much deeper than that, but that will be maybe for a few videos on in this sequence. Right now, I just want to see where we have gotten to compared to what we did with like the Conway stuff, and what's next. Well, for example, f omega plus 2, what we can see is it's this process of repeatedly doing these these f3s, which were chains of exponents, and then put them into that, and then put them into that, and put them into that, put them into that. Well, if you actually unpack it, I'm not going to go through the details, but if you actually kind of compare with what we were doing with the chained arrows, that's really very, very similar. And so, in fact, this f omega plus 2 level of n, it's very similar to, but a bit bigger than the idea of a chain with, you start with 2, because these are all based on doubling from the very start, and then it turns out it's n, and then n minus 1, because there's this annoying kind of n versus n minus 1 thing, and then it's k plus 1. I'm sorry, 2 plus 1, 3, there we go. I'm reading off the Wikipedia thing. As you can see, I've got this handy little reference from Wikipedia. So, right, so it looked like we had the 4 chains were started showing up at f omega plus 1, and then f omega plus 2 was we repeat that, and that feeds into the wonderful diagonalization process. It turns out that that's exactly it's about as far as we really meaningfully got with the Conway chained arrow notation. 4-term sequence with a 3 on the end, because that's repeated stuff with 2s, and that's repeated stuff with 1s, and that brings the chain down to 3 chain, and a 3 chain was the arbitrarily powerful Knuth up arrow notation, kind of iterated over and over again. So this is about the level we've got to with f omega plus 2. And of course, we can go to f sub omega plus k for any k. And that's just defined by f sub omega plus k minus 1, if we've already understood that, and repeated n times of n. And then the beautiful thing, of course, is when we strip that down, so that's going to be f sub omega, plus, it doesn't like that, plus k minus 1 of f sub omega plus k minus 1 of dot 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 of, and then one last one, f of omega plus k minus 1. And then let's expand out the last one. Okay, that's f sub omega plus k minus 2 of n. So there's going to be n minus 1 of these guys, and then the last one I changed, and then that's done n times. The last omega plus k minus 1 I changed into n copies of this one. Okay, but the last one of that expands into n copies of the previous one, and the last one of that. And I haven't even expanded these guys out because it's not their turn to even operate yet. But eventually this guy is going to step up to the plate and say, oh, the definition of this is in terms of omega plus k minus 2, and that's in terms of omega plus k minus 3, etc., etc., etc. So you're going to get an immense number of function applications of these very, very powerful functions based on, and each time you do it, the number of applications is based on what number comes out of this immense function. Just truly staggering. Now, the Conway chained arrow notation we know is very, very powerful. And so it turns out, again, if you unpack it and combine it, we'll just cheat and look at the Wikipedia thing, is it's a bit bigger than 2 arrow n minus 1 arrow. It turns out to be k plus 1. So we have, with these kinds of guys, where we just use a little tiny bit of ordinal arithmetic, we have gotten up to the level of a Conway 4-chain, with almost arbitrary values. This has to be a 2, but it's not that crucial. This guy is really the thing that blows up the value of a Conway chain, not so much this guy. Okay. Now, let me look at this. This is the Wikipedia article. It's called, I'll show you. It's called Large Numbers, and it's the section that's entitled, it's a very nice little section, it's entitled Systematically Creating Ever Faster Growing Sequences. And it's linked from the chained arrow article. Okay. And so here's the doubling, here's the repeated doubling, 2 to the n times n, here's f3, and then fk plus 1, and so this is where we get to the level of the up arrow repeated, and then here's where we introduce diagonalization, and that's so where the n goes into this argument and not just that argument. Turns out it's related to what's called the Ackermann function, which is a famously fast-growing function, which is was really used, interestingly, in the foundations of mathematics. I want to mention Graham's number here. You can go ahead and look at that in Wikipedia if you want to know more. That's famous for being supposedly the largest particular number that was ever used in a real mathematical proof, a significant mathematical proof. And what that is you start with 4, and then you take 3, quadruple up 3, and then you put that in the arrow slot. So you do 3 that quadruple, or that how many arrows up 3, and then again and again. So you can see it's this process of 3 up arrow, up arrow, up arrow, up arrow, nested up arrows. And that's exactly what we were getting with f omega plus 1. It replicates iterated up arrows, or in other words, these kinds of guys from the Conway with a 2 at the end. And so we've gotten way past Graham's number. So f omega plus 1 with not a huge number put into it gets way past that. And now we're at like f omega plus k. And so we're at this level where we get to these 4 chain sequences. Okay. Now it has this funky thing, f omega 2. What on earth would that mean? Well, let's go back to ordinal arithmetic. Back to just, what was the idea of omega? Remember, it was a bunch of these stars put in order. Well, I'm going to rewrite that a little bit. It's the limit of just n, of all the finite numbers. And so I'm just going to say limit of n just means make n arbitrarily big. Just keep going. So it's just 1, 2, 3, 4, 5, and that's a sequence which, if you let it go forever, it approaches omega. And so that's going to be our new understanding of how we do these ordinals. If we have basically an unbounded sequence, we just say, okay, the limit is just what the trend is. Even if it's infinite, we just say, okay, we've maybe defined a new infinite quantity. I know I'm being fast and loose, and you can make it a lot more precise, but I don't want to. Okay, so here's omega. Remember, this was omega plus 1. Omega plus 2 would be put another star here. Omega plus 3, put another star here. Well, here's omega times 2. It's just omega put next to itself in the pictorial version. If we want to be a little more official than that, it's the limit of omega plus a finite number. So I take this whole thing that's already set, and then I add 1 or 2 or 3 or 4, and then I look at the limit. The reason that's important is what I'm really defining is called a fundamental sequence for omega 2. I need to not just be able to talk about omega 2, but I need to be able to use the diagonal argument on it. And so I need to be able to say, if I'm looking at omega 2, what were the things that kind of led up to it? So here's how f omega 2 is defined. F sub omega 2, that's just omega times 2. It's not supposed to be special. You just often don't write the times marker. Of n, we use the diagonalization trick here. Because of omega 2, it isn't just something plus 1. We can't use the repeater trick, the recursion trick of, okay, just decrement this one and repeat the previous level n times. This is what's called a limit ordinal, just like omega was. It's not something that's just the immediate successor of anything, basically because of this last arrow. But that's exactly where the diagonalization trick works. So I'm just going to say that's f sub omega plus n of n. And that's pretty powerful, because we can see that as I increase this number, 2 to 3 to 4 to an arbitrary k, these guys get immensely powerful, because they nest all the ones before them. And now I'm doing the diagonalization again. So I'm doing diagonalization again. Okay. So for example, f sub omega 2 of 3, well, that's just going to be f sub, it's really not that powerful yet, because it actually just goes back to f omega plus 3. Now, if this had been 100, it would be f of omega plus 100, which would be immensely powerful, even by our new standards. But with 3, it's not incredibly huge. Okay, and that is just, that's the kind of thing I was doing. Well, I did f omega plus 2, but it's not a lot more complicated than this. It expands out in terms of f omega plus 2s, that expands out in terms of f omega plus 1s, and of course you get a fantastically, immensely huge number. But remember, the combination was the really powerful thing. What if I do f sub omega 2, and it totally makes sense to add a 1 to that. I just put a star right here. Okay, that's a perfectly well-defined ordinal number. F omega 2 plus 1 of 3 equals, okay, that's f omega 2 of f omega 2. It's done 3 times. F omega 2 of f omega 2 of 3. Okay, that first one just evaluates to this guy. So let's copy and paste. That first one is just, oh yeah, f omega plus 3. Okay, I know that's more powerful, a more faster growing function than anything I've seen in my life up until the last 20 minutes. But it's just f omega plus 3. Somebody else could beat me with f omega plus 100. But look at what's going to happen now. That's going to be, let's leave the f omega 2 on the outside unevaluated. Remember, f omega 2 is a limit ordinal, and the definition was take this and just put a plus that. So I take this incredibly huge number, and then I do f omega plus that incredibly huge number of that huge number. And only when I've done that do I do the same process with f omega 2. Okay, so again, the combination of diagonalization and then a little bit more of the standard recursion and repetition is just staggeringly huge. Okay, so we're getting really, really seriously big here. So let me show you the Wikipedia page again. So the claim is that f omega 2 is exactly, or f omega 2 plus 1 is something where we're getting to not only 4-stage repetition, but 4-stage repetition where all of these guys, none of these guys are just numbers anymore. N, 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 K. And that's actually, I think, a significant underestimate. Okay. And we can go further than that. We could go to f sub omega 3 of n. Okay. What is that going to be? Well, omega 3 is just the limit, as n goes off to infinity, of omega 2, that's not what I wanted to do, f omega 2 plus n. Okay. So all these new ordinals, these kinds of limit ordinals, are defined in this way. And it's really just like ordinary arithmetic, except with a few limits put in. Multiplication is defined in terms of repeated addition. And I just take omega times 2, which I already understand, and then I just keep adding more and more and more finite numbers, and I look at the limit. Okay, so given that, our diagonalization trick says just pick the nth term of this guy. So that's f sub omega 2 plus n of n. And so that's going to give us access to arbitrarily large omega 2 pluses. And we know that those guys give us incredible nested repetitions of f omega 2s, which then give us immense nested repetitions of f omega plus k's, which in turn eventually expand in terms of actual powers. So over here it's saying f omega 3, that's where we finally put n's into all of these guys. So we're still on the 4 chains, because really 4 chains are immensely powerful. It's really amazing that this notation can survive in a head-to-head competition almost with something as powerful as f omega 3. But now we're going to really take off. F omega k of n. Omega times k is just the limit of f omega k minus 1 plus n's, and so that's going to be f sub omega k minus 1 plus n of n. So I look at, like, to calculate f omega 7, it's going to be f omega 6 plus as big numbers as we can imagine. Whew! So it turns out, and I'm not going to show you the comparison, I haven't actually worked it out in detail, but it's totally plausible, that at this level we're now beating any fixed length chain of the Conway chained arrow notation. you put k plus 1 n's together, and you've got f omega k. Not even close. I mean, not even quite. It's somewhat comparable in terms of the idea. Okay. Now there's one more down here. F omega squared. Huh. What does omega squared mean? Well, let's think about this. Okay. Omega squared is just if I take omega, and then omega times 2, and omega times 3, and omega times 4, and I look at the limit of that. It's very conveniently represented as just a quarter plane worth of stars going infinitely that way and infinitely that way now. And so it's just the limit as n goes to infinity of omega n. Okay, that's another thing we're going to diagonalize. Okay, so how does that work in terms of our fundamental sequences and our fast-growing function? F omega squared of, let me just do 3. That's going to be f sub, now omega squared is just the limit of omega times 1, 2, 3. Okay, that's just going to be f omega 3 of 3. Okay, now let's unpack that a little bit to show you again how it works. That's omega 2 plus, and that was supposed to be omega 2 plus an arbitrary n, but the rule is I always just diagonalize. I just take that number. If I ever need a limit with an arbitrary n, I just take this number and I put it in. Oh, okay, omega 2 plus 3 of 3. Okay, well that's actually a plus. I can actually expand that out. That's 3 copies of f omega 2 plus 2, the previous one. Okay, now that's going to be, I hope this isn't too tedious, but it's just good to actually get this out. I'm going to take 2 copies and leave them alone. And then I'm going to turn the last copy, the closest to 3, the first gets evaluated, into 3 copies of, I can't do that. There we go. 3 copies of omega 2 plus 1. And so on. Eventually it'll get down to f omega 2, which is diagonalized in terms of like f omega plus 3, and then f omega plus 2, f omega plus 1. And again, eventually it gets down to powers after an immense amount of time. Okay, so this is pretty staggeringly huge. But once again, it's not so huge compared to f omega squared. If we just go even one more than that, that's where it gets, again, more powerful because we're combining. That's 3 copies of f omega squared. And now the first copy sees a 3, which is big enough. Trust me, it's a huge number. But then that cycles into another f omega squared, which is just fantastically huge. Huge! Okay. So f omega squared plus 1 is going to be utterly big. Now f omega squared itself, it turns out, let's go back to Wikipedia. F omega squared is where we get pretty close to the end of the line for Conway chained arrow notation. F omega squared n is just f omega n of n, if you believe this, that this is f omega k of n, that it's a chain of, in fact it turns out to be n plus 1 n. So it's an arbitrarily long chain. It's a chain where not only the number we put in is in here, but it also tells you how long the chain is. We got a little bit further than that by putting like superscripts on the arrows and saying, well, what if I could use arrow notation to talk about how many arrows there are? Trust me, we'll get there if you bear with me. I don't know how many people are still with me at this point. But this one, f omega squared, is pretty darn impressive. So we've gotten a little taste of ordinal arithmetic, the idea that we can actually add, multiply, and exponentiate ordinal numbers. And that's a very cool, important subject in itself. It's really, really basic for set theory and logic and what's called proof theory. But for us, it's been mainly an excuse to label cool ways of doing the repetition, recursion, and diagonalization tricks to create utterly, utterly huge numbers out of just the number 3. Now, you might think this is kind of cheating, and in a way it is. The goal was to create functions and notations that created unbelievably, ridiculously huge numbers. And you might think that using infinity as a tool in that is cheating. And if you think that, oh well. But what we're really using infinity as is we're not actually taking infinity and putting it into this function as an input. That would be stupid because we just get infinity. We're using it as a system of organization of recursion. And it's really a profound fact that when you look at how recursive reasoning and reasoning at a very deep level can be organized, it turns out to be intimately related to ordinal arithmetic. And we'll get a tiny little taste of that, I think, if I go further as far as I think we're going to go in these videos. It's a good place to stop for now, though.